next problem is problem 8.176. So here I just copied over the sketch of the problem, and I also wrote down the important values that we were going to need. So the flow rate, which is going to be 600 gallons per minute. Now the next thing to do is that we can do some quick little conversions just to make our further calculations a lot simpler. So this 600 gallons per minute can be converted to 1.33 cubic feet per second. Because we know the desired volumetric flow rate, we can also find the average average velocity profile, since we're assuming a constant area cross section throughout the piping. So this means that our velocity profile is going to be 15.3 feet per second. Finally, knowing the velocity, we can also now find the Reynolds number, which is going to be 4.1 times 10 to the 5. The next step is to write our Bernoulli equation, considering our minor losses and our major losses in the system. Now from the point 1 and 2 drawn on the sketch here, we know that we're both going to be pumping from atmosphere to atmospheric pressure. So the variation in pressure will be 0. Also at point 1, we assume our body of water is large enough, so the velocity at point 1 will be 0, and also our initial height will be 0. What we obtain is that we have minus our velocity at point 2 over 2 minus gz2 is going to be equal to the minor losses and the major losses of the system. Now the pump can be seen as a negative of a loss, and so we can rewrite this expression as the work put into the pump is equal to V2 squared over 2 plus GZ2 plus our major losses and then our minor losses. Now here I rewrote our minor and our major losses by factoring out the average velocity squared. And then inside our brackets here we have our frictional losses by the length of the pipe plus the summation of our major losses, and then plus our summation of our minor losses. Now because we know our pipe is made of aluminum, we could find the relative roughness as being 1.5 times 10 to the minus 5, and using the Reynolds number that we computed earlier, we find that our friction coefficient factor is 0.0135. The next step, so for our minor losses, the minor losses that we have in our system is the K from our reentrant and the K of all the joints. The K of the reentrant is given by 0.78, and then all the joint losses are given by a K factor of 1. We gotta remember that we have 15 of them, so times 15, that gives us a total minor losses coefficient K as being 15.78. Now onto the major losses of the system. We have the globe valve. We also have the 90-degree bend before the pump, and we have two 45-degree bends, one right after the pump and then one just after the just before the outlet. Now looking at table 8.4, our equivalent length for our gate valve is 8. For an elbow joint, it is 30. And for a joint that is at 45 degree, it is 16. Placing all this together, we get our major losses as being 0.945. Now we can retake our Bernoulli expression as found earlier and replace it in with our minor losses and our major losses in the system. And what we obtain is that the H of the pump is 2.53 times 10 to the 4 feet squared divided by second squared. Now it is important to remember that we have only a 75% efficiency rate of our pump, which means we're going to have to put in more power than we actually need. This can be calculated by the work is equal to the mass flow rate times the H of the pump divided by 0.7, which is our efficiency. Now the work required for the pump in pound feet per second can be written in horsepower by divided by 550. And so we obtain that the required power into the pump is 170 horsepower. Now the other part of the question is also asking for the pressure at the outlet of the pump. So here we will again take Bernoulli's equation, but I will be simplifying a lot of the steps here, so that we just have P3 minus P1. So that means our variation in height we assume is going to be 0. Also our variation in velocity is going to be 0, and we also will assume that we don't have any losses, which is incorrect because we know we have that 90-degree bend, but we'll say that for the sake of simplicity that our variation in pressure here is just going to be equal to the power that that the pump is outputting. And what we obtain here is that our variation in pressure is going to be 341 psi.